There is no single best local language model for every user. A useful choice depends on the task, hardware, memory, speed, context, output quality, concurrency, privacy, and operational tolerance for slow or unstable behavior. Local inference is a hardware-constrained engineering decision. The complete configuration includes model architecture, parameter count, quantization, context size, runtime, acceleration backend, offload, prompt template, generation settings, and cooling. A model that leads one public benchmark may perform poorly on a specific machine or task. Benchmarks use particular prompts, scoring methods, hardware, software, and settings. They are useful for forming a shortlist, not declaring a permanent winner. Quality has several dimensions: factuality, instruction following, coding ability, writing style, domain performance, refusal behavior, hallucination risk, and consistency. A larger score or parameter count does not guarantee the behavior an application needs. Performance also has multiple dimensions. Time to first token matters in interactive use. Generation speed affects reading pace. Prompt processing matters for long documents. Throughput and stability matter for batch jobs and multiple users. The best choice is the smallest or simplest configuration that meets the real requirement with acceptable quality and margin. Start with the task and machine, test representative work, and scale only when measured shortcomings justify it. Include total operating cost in the decision: hardware purchase, electricity, cooling, storage, engineering time, maintenance, downtime, and review effort. A free model can still be expensive to operate badly. The CPU supports tokenization, application logic, and inference when layers remain on the processor. Core behavior and memory bandwidth influence CPU performance. CPU-only systems can run useful smaller quantized models, but may have lower generation speed. A discrete GPU provides parallel compute and dedicated VRAM. VRAM must hold model weights, cache, activations, and runtime overhead for accelerated work. The operating system and display may also consume part of the available memory. System VRAM supports the operating system, applications, model loading, CPU resident layers, and cache. Unified memory systems share a pool between CPU and GPU. Shared capacity can increase flexibility, but bandwidth, thermals, and total memory still limit performance. Storage affects download capacity, startup, model switching, logs, and backups. Keeping several parameter sizes and quantizations can consume substantial space. Fast storage cannot compensate for insufficient working memory during inference. Power and cooling determine sustained behavior. A laptop may benchmark well briefly and slow under heat or battery limits. Desktops offer easier cooling and upgrades. Many PCs trade compactness for expansion and thermal constraints. Apple Silicon, NVIDIA, AMD, and CPU-only systems use different acceleration paths and software support. Inventory exact hardware, available memory, operating system, drivers, power mode, and cooling before using someone else's performance claim. Use available memory, not the number printed on a product page. Displays, operating systems, background applications, security tools, and other services reduce the capacity the runtime can actually allocate. Model size is often described by parameter count. Labels such as 3B, 7B, 8B, 14B, 32B, and 70B indicate billions of parameters, although architecture and implementation affect actual memory, quality, and speed. Smaller models usually load faster, need less memory, and generate more quickly. They can be excellent for classification, rewriting, extraction, short assistance, narrow domain workflows, and high-volume automation when evaluated carefully. Larger models may offer stronger reasoning, knowledge, instruction following, or difficult task performance, but they require more memory and compute. They may also increase latency, power use, deployment cost, and the consequences of concurrency. Bigger is not always better. A large model running mostly on a slow CPU or constantly near memory limits may be less useful than a smaller model fully accelerated with room for context and other applications. Model family matters alongside size. Training data, architecture, tokenizer, prompt format, specialization, licensing, and alignment can make two similarly sized models behave very differently. Compare task results, not parameter labels alone. Architecture can also change compute and cache behavior. Two models with the same headline parameter count may need different memory, context overhead, prompt formats, or runtime support, so size categories remain planning approximations. Plan for the whole workload. A model that fits for one short prompt may fail with long context, vision components, multiple sessions, or large outputs. Keep memory headroom for cache, runtime, operating system, and recovery from bursts. Quantization lowers numerical precision, so a model uses less memory and often runs more practically on local hardware. Labels such as Q2 through Q8 describe broad precision levels, but exact schemes and model behavior differ. Lower bit quantization generally reduces file and memory size while increasing the chance of quality loss. Higher precision uses more resources and is not automatically better for every task, runtime, or machine. Test the actual file. GGUF is a common local model format for llama.cpp compatible runtimes. Compatibility depends on architecture, runtime version, tokenizer, prompt template, metadata, and acceleration backend, not only the file extension. Memory fit includes model weights, key value cache, context, batch settings, concurrent sessions, runtime overhead, display use, and other applications. File size is therefore not a complete VRAM or unified memory estimate. Some runtimes allow different cache precision or memory strategies, creating another quality, compatibility, and capacity trade-off. Treat those settings as part of the tested configuration instead of assuming model quantization tells the whole story. Partial GPU offload can run some layers on the accelerator and leave others on the CPU. This may make a larger model load, but transfer and CPU work can reduce speed. A technically successful load is not an operational success. Avoid configurations that consume nearly all available memory, swap heavily, crash on long prompts, or throttle under sustained work. Compare several quantizations and sizes with realistic context, then preserve a margin for stability. Context is the token sequence available to the model for the current request. It includes instructions, conversation, documents, code, tool output, and generated history. Longer context increases cache memory and prompt processing time. Short chat and rewriting usually need modest context. Long document analysis and summarization may need more, but retrieval or chunking can be more reliable than placing an entire archive into one prompt. Coding workloads vary from a small function to repository-wide analysis. Useful context depends on file selection, language tools, and the model's ability to use distant information. Maximum context does not guarantee maximum understanding. Retrieval-augmented generation adds selected source passages to a prompt. Its workload includes embeddings, indexing, retrieval quality, context assembly, and citations. Agents add tool calls, state, repeated prompts, and potentially long histories. Vision language models add image encoding, visual tokens, adapters, and image memory requirements. Batch processing and multiple users multiply cache and compute demand. The same base model can behave very differently across these workloads. Size context for the actual application and cap unnecessary history. Measure prompt processing latency, cache growth, accuracy, and failure behavior. A smaller context used with disciplined information selection often outperforms an oversized, noisy prompt. Define a workload envelope with typical and worst-case prompt length, output length, images, tools, sessions, and request rate. Capacity planning needs that envelope, not one carefully chosen demonstration prompt. Tokens per second approximates generation speed after processing. Time to first token includes request setup and prompt evaluation before visible output. Prompt processing speed becomes especially important for long documents, code, and retrieved context. Latency describes how long one request waits, while throughput describes total work completed across time. A setting that improves batch throughput may increase interactive latency. Multi-user services require queue and concurrency measurements. GPU offload can accelerate supported layers or operations. CPU fallback allows models to run when accelerator memory is limited, but it may reduce speed. The best offload level depends on memory, bandwidth, runtime, and workload. Thermal throttling reduces sustained clocks when heat or power limits are reached. Monitor performance over a long enough test to expose it. A short cold start result can misrepresent a laptop or compact system. Benchmark end-to-end tasks, not only generation. Include model load, prompt processing, first token, output, structured parsing, tool calls, and failure recovery where relevant. Record memory, power, temperature, and errors. Set practical expectations. Interactive writing may tolerate one speed, batch summarization another, and agent automation may care more about task success than raw tokens. The rate model delivers acceptable work within the user's patience and system capacity. Measure variability, not only averages. A system with acceptable average latency may still produce long pauses during large prompts, model switching, concurrent requests, cache growth, thermal throttling, or memory cleanup. A general assistant needs balanced instruction following, writing, knowledge, conversational behavior, and safe handling of uncertainty. A compact model may be sufficient for routine local help, while difficult analysis may justify a larger option. Coding assistance should be tested on the actual languages, repositories, context sizes, completion style, debugging, and tool workflow. Benchmark correctness and edit quality rather than relying on generic chat results. Writing and editing need tone control, preservation of meaning, revision quality, and consistent formatting. Cybersecurity analysis needs careful evidence handling, domain vocabulary, defensive framing, and low tolerance for invented indicators or commands. Document review and retrieval need source grounding, citation behavior, extraction accuracy, and long context discipline. Private assistant use adds requirements for logs, access, local integrations, and data retention beyond model quality. Vision language workloads need image understanding, visual token budget, OCR, counting, chart, or screenshot performance, and additional memory. Automation and agents need tool selection, structured outputs, error recovery, and resistance to compounding mistakes. Select model families by demonstrated task fit, license, runtime support, language needs, and operational behavior. Maintain a fallback when one model is too slow, too weak, or unavailable. One model need not serve every workload. Create a small local benchmark set from real work. Include common cases, difficult cases, costly errors, expected formats, and privacy-safe examples. Write acceptance criteria before seeing model results. Keep the configuration reproducible. Model, quantization, runtime, backend, context, prompt template, generation settings, hardware, drivers, and date. Changing several variables at once makes results difficult to interpret. Run important prompts more than once. Record accuracy, completeness, refusals, hallucinations, formatting, latency, prompt processing, generation speed, memory, temperature, failures, and recovery. Stability is a quality characteristic. Evaluate whether refusals are appropriate and whether the model invents facts, citations, code behavior, or security conclusions. A smooth answer can still be wrong. Use task-specific review or automated checks where they are valid. Compare total workflow value. A smaller model may finish more tasks correctly because it is fast, stable, and easy to retry. A larger model may reduce review on difficult tasks enough to justify its cost. Keep an evaluation log and define promotion or rollback criteria. Retest when models, quantizations, runtimes, drivers, prompts, or hardware change. Choose based on evidence from the actual machine, not memory of an old leaderboard. Choose local models by hardware fit, task fit, memory, speed, quality, stability, privacy, and operational needs. No parameter count, benchmark, or model family is universally best. Inventory CPU, GPU, VRAM, unified memory, system RAM, storage, acceleration support, power, and cooling. Evaluate the complete model, quantization, runtime, context, offload, and concurrency configuration. Smaller models can be faster, stable, and excellent for focused work. Larger models may improve difficult tasks but increase memory, latency, power, and deployment complexity. Quantization and context reshape those trade-offs. Benchmark representative prompts repeatedly and record quality, refusals, hallucinations, first token delay, prompt speed, generation, memory, thermals, failures, and workflow success. Start with a smaller reliable model, then scale when measured shortcomings justify it. The best local model is the one that performs acceptably on the actual machine for the actual tasks with enough margin to operate.